Hi everyone, welcome back to my structural analysis video, and in this case we are going to analyze a rigid frame using with the same software that we have used in our previous video, the STAAD Pro version 8i. In this case we have this problem, which is a rigid frame with our assumptions of the following materials. We have the modulus elasticity, unit weights, and etc. So also we have given loads, load combinations, and the section properties that will be our basis in assigning them in our software. So basically this figure here are going to be will be our basis, our reference figure in plotting the structure using our software. And same principle, we are tasked to determine different values: reaction, vertical, horizontal forces, shear, the moments, the actual forces, and etc. With respect to the specific type of loadings, load cases, and specific beam or to which the load cases, the load combinations take effect, or what are the effects to them. So let's proceed to plotting our figure. Okay, so this is our software. What we have to do now is to create a new project. It's actually a space, you can for me you can actually check plane or space, and I'm gonna name this C, which is a rigid frame. This is C underscore rigid frame. And yeah, if we should check our units, since it is in a metric unit, so that's it, or the SI unit. So our units should be in meters and in kilonewton for the force units. So let's proceed next. And after this, instead of adding a beam, I would like to open the structure wizard upon entering the command window of the software, in order for me to manipulate or just easy establish a structure using the present existing structural modes. So by clicking finish, it will direct me to the command window, and it's actually taking a moment, and then it will lead me to the structural wizard. So we have these models, and in this case we are going to use the frame models, and it's a bay frame. Just double click, then I'm gonna input the parameters of our given. Actually it's 10 along the length, along the x-axis it's 10 meters. Its height it's 9 meters, and its width, since it's actually just two-dimensional, it is necessary to imply that there's a three-dimensional or offset or something like there's a three-dimensional face of the structure. So I'm just gonna input this as 0, along with its number of base on width, it's 0, and number of base along length is actually 2 and 2, and then I'm gonna edit this since we have it in our parameters. So bay1, that's actually 6 along the length, along the x-axis, and we have 4 still along the length. That's 6 plus 4, that makes it 10, so that's logical. So click OK, and then number of base along height is actually 2, but we have to edit the length, since it has been specified in our structure. The bay1, that's actually 5 meters, and the bay2, that's actually 4 meters, that makes it 9. So click OK, then we click apply, and after that it will show us the structure. And then I just have to click X then it will ask me to transfer the merge or transfer the prototype to the main command prompt or command window. And then if you go back, I will be able to put it in the window, or as the command. So I'm just gonna view it in front view. As here we can see, let me check the dimension if these are correct. So dimensions display. So here, if you're going to compare with our reference structure, that's 5 meters, 4 meters, 5, 5, 6, 4, That's correct. However, there's an excess of the structure, so I'm just gonna highlight these nodes and beams here, and just gonna delete them since they're not included. Yes, and so we have our structure. And after that, as a basic, after creating the structure, the frame structure, we're going to assign a support. So I'm gonna go to the general, then click supports. So as from our reference structure, point F, G, node F and G are actually fixed support. So the corresponding nodes for that, I'm gonna view them. Let's click the labels, and then I'm gonna show the beam numbers and the node numbers in order for us to later on have the convenience in comparing and actually giving us a directive to which beam or nodes are we going to analyze with specific aims, no, asked from us in our problem. So we just click apply and then OK. And since those dimensions are settled, I'm just gonna remove those dimensions and remove, and then remove. Okay, so they're no longer present. After that, we're going to define our apply our supports. Supports are actually at node 1, 2, and 3. So we create. So those are there are two types of support that's present in our structure: the fixed and the pin. So those are actually present by default. So I'm just gonna add, and then create another support for the pin support, and then add. Then I'm gonna click the support 2, which is the fixed support, and I'm gonna highlight this and then assign. Then click yes, and then it will assign the support. Then for support 3, that is the pin support, it's actually at node 3, corresponds to node H in our reference structure. So I'm just gonna highlight the node 3 and then assign, and then click yes, and then there we have assigned our supports. And after assigning the supports, I'm gonna go and define the properties. Or there are actually different properties of the beams. There are two types of beams here. Of the base are actually columns and beams. So before assigning those, for my convenience, I'm going to group the beams into beams in the columns in the columns. So to do that, it's actually asking me to save it in order for me to not lose what I have started and what I have created during the process. So I'm just gonna view. Excuse me. Select. So beams parallel to the x-axis. So it's going to highlight the beams. Then I'm gonna click Ctrl G, and that will allow me to define the group name. So it will group those highlighted beams. So I'm gonna say beams. Then there's our beams, and then click OK. So we're ready, and then create another. I'm gonna again select, but in this time the beams are parallel to the y-axis. So that should not include the x-axis since we are grouping the columns. Same process, Control G, then create a group name that is for the columns, and then still beams, then OK, then check. So if I'm just have to associate them, and then this associate, then OK, close. Excuse. After that, upon assigning our properties later, if I already have assigned the properties, I just have to click G, and then click these groups, and then highlight, and then it will make inconvenience in assigning the properties, since there are two sectional properties for the beams, and there are difference for the beams and the columns. So let me assign now or define the properties. So our properties are actually for the cross-sectional properties. So this are for the columns is 400 by 400 mm, and for the beams it's 250 by 350 mm. So for that, I'm gonna define it. Basic definition, and it's a rectangular. So this is a concrete. So 0.4 point 400 mm equals to is yeah 0.4 meters. Then pick a sign. Then next is the 0.35, that's 0.35 or 350 0.25 mm beam. Let me check, double check. 0.25, 0.35. Okay, then we click assign. So excuse me. Excuse me, sir. The material here is concrete, so basically there are assumed properties, the unit weight, and etc. And I am actually using the materials here default at the concrete material, since they're actually the same, and maybe there are some difference in points, but they're actually the same. So close. That won't make any maximum effect, or you may I mean kanang big difference on the resultant analysis. So I'm just gonna close this. Yeah. Since I have I accidentally assigned the excuse the wrong cross-sectional properties at the columns. So it's supposed to be 0.40, so I'm just gonna reassign, highlight the columns, and then this should be the then highlight again. I'm just gonna highlight the columns, then I'm gonna assign. So there, so we have assigned our cross-sectional properties for the columns. For the beams, same process. You just have to tap this property for the concrete for the beam. So I'm just gonna highlight the beam. Oh, there's something wrong. It's actually wrong, so I'm just gonna delete this. And the columns, and for the columns. I'm just gonna create new, since I actually inputted it wrong. So name beam. Same process. Beams parallel to the x-axis, then Control G, then create beams. Those are not beams, and then click OK. So, then after that, highlight, and then we assign the concrete material. Then click assign. Control G, and I'm having some errors here. I'm gonna delete it and create a new again. Something's wrong. Select beams parallel to the x-axis, then Control G, then group beams. Click OK, and then associate to list, associate, close, then assign. Control G, then beams and assign, associate, highlight. No. Let me just fix this. Select. Select beam spiral to the x-axis, and then Control G, and I'm gonna group this. Create a beam, then beam, and click OK. Associate, then close. And after that, I'm gonna assign the properties to that highlighted. There. I really had trouble doing that. Okay, so after that, we have assigned our properties. So what we need to do now is to actually verify it from our. I like doing this because it will make me more convinced and justified that I already have assigned the properties, though it's actually present in the window. So the indication that you have already assigned the properties given with the sectional properties that you have created, you have defined, this will actually create a dimension or a render view, like this. So you have the thickness, the width, the length, and the height, compared to the unassigned sectional properties. It will only render a line view, just straight lines of connected lines of connected beams, connected lines that represent the beams and the nodes. So after that, I'm just gonna X this, so that's already verified. So what we need to do now is to apply the loads. So now our loadings, we have the dead loads, the live loads, and we have the load combination. There are two cases, the case 1 and the case 2. So let me go with first assigning the dead load. So in the dead load, we have the dead load. I'm gonna add the dead load. So this type is the dead load, and we have DL. I'm gonna DL. I'm gonna add again the live load. That's LL, and the wind load. That's WL. Add. Okay. After that, I'm gonna close. Then I'm gonna define. I'm gonna add a loadings, for the dead load. And first, before applying the given dead load is 31 kilonewton per meters, I'm gonna first generate the self-weight load. That's factor -1, then add. It's already there. And then a member load, that is a uniform force, that is actually 31 kilonewton. It's only along, according to the description here, it's applied in all beams, so it's not included in your columns. So 31, that's going downward, so that's -31. -31, and then click OK and add. Okay, so we have defined them. So I'm gonna apply the self weight. So I'm gonna Control G, then highlight the beams. Yes, asking me to save it from time to time. The beams, and highlight the beams. Then I'm gonna assign the self weight. To the highlighted beams. Assign to the selected beams and plates, etc. I'm gonna assign and click yes. And we have assigned our self weight. Next is we're going to assign the applied the dead load, that is 31 kilonewton per meters, and assign to the selected beams, and then click assign. And there we have assigned our self weight and the 31 kilonewton that is given. And after that, the dead loads and the live loads are actually assigned in all beams. So from here, we're going to define our live load. Just have to add our live load, and let me close this. From our problem, our live load is applied at the upper and lower level from the left side of the structure. That's at node A and C. So there are actually two live loads, that 40 kilonewton at the top and 20 kilonewton at the bottom, at the lower level, that is 4 meters from the top. So that's at node C. So with that, I'm gonna add a live load, that is a nodal load. So it's a nodal load. Then along the x-axis going to the right, so it means it's positive. So I'm gonna input 40 kilonewton, then click add. And then since I already have added that force, I'm gonna add 20 kilonewton and manually assign it to the nodes. So I'm gonna click this, then I just have to highlight this node here, highlight the node, and then click this, and then assign to the selected nodes. Then click proceed, and there we have assigned our 40 kilonewton at the top. And then next is we're going to assign our 20 kilonewton at our node C, corresponds to the node 4 in our beam. Then after that, I'm just gonna click this and then highlight the beam, the node 20 kilonewton, and then click assign to the selected nodes, and then click yes. There we have assigned it. So after this, I'm gonna edit the label orientation, beam numbers. You can leave it like that. So after that, general, we need to click the general, close it. We have already assigned our loads, for the dead loads, live loads, and for the wind loads. Okay, let me live loads and the wind loads. I know, we had a mistake. This should be assigned at the wind load. Sorry, that was a mistake. The live load, our live load is only assigned to all the beams, and it has a value of 10 kilonewton per meter. So I'm gonna add, it's a member load, it's negative 10 kilonewton per meter, and hit add and then check. Then just gonna highlight the beams, highlight, and there. After that, now we're going to apply the wind load. What we had done a while ago is actually the application of the wind load, 40 kilonewton from the topmost portion of the structure, and from the topmost portion of the structure, that's 4 meters going down or lower, that's actually the 20 kilonewton wind load applied. Excuse me. After that, we add what we have done a while ago. Just have to repeat it. It's a nodal load. It's actually that's 40 kilonewton going to the right, add, and then 20 kilonewton going to the right again and add. So same process, it's a nodal load, so I'm just gonna click this, highlight the node, then assign to selected nodes, assign right there, then highlight this node 4, then assign. There we have assigned our dead load, live load, and the wind load. Next is we're going to make or to define our load combinations. In the load cases, we just have to add load case, define combination. So our factor, we're just gonna add a dead load, live load for combination, and name this case number 1. Our factor for the dead load is actually 1.5, if I am not mistaken. I'm on 1.4, and then 1.7 for the live load. Then click add, and then next is case number 2. For case number 2, that includes the dead load, the live load, and the wind load. So our factor for that is, for the wind load, for the dead load, our factor is 1.05. So I'm just gonna edit it and put for the live load of 1.275. 1.75, same, 1.275. Then click add, and so we have add our load cases, the load case combination 1 and 2. so we can actually see it from here. So what we're going to do now is to actually, yeah, those are already assigned now, and then see it from here like that. So if we're going to tap this this combination, you can actually see the structure like that. I mean the load applications, or how the loads are applied according to the combination factors. So after that, let me try to run an analysis. Let me do the analysis print, then add, and then close, then click OK. Then after that, hopefully this will run softly without errors. So just run analysis, asking us to save it again. No, we have no errors, there's one warning. So well, that's fine. Go to processing mode and then select it and apply, then click OK. There we have our analysis. So let's go defining, or actually identify what we are tasked to, or identify the values, specific values. So the first value that we are going to identify is the reaction of the support due to the dead load, the vertical, horizontal, the moment of the support. Support F that actually corresponds to the node 1. So node 1, click reactions. So due to the dead load. Since due to the dead load, so here we can see that our values for the vertical force along the x, y, and we have the moment at F. Actually, we can see all the values in this table. And the node 1 for the dead load, so these are the values. For the horizontal force, horizontal reaction, or along F of x, that's 7.633. So I'm gonna input it here, 7.633, and for the Fy, horizontal force, let's check if it's in the dead load. 194.158 kilonewtons. 194.158 kilonewtons. And then for the moment, that is negative 10.647. Negative 10.647 kilonewton dash meter. Then I'm gonna save this because I'm going to submit this. So after that, we move to other required values to be acquired in our structural analysis software, giving me this analysis results. So the end moments of the beam CD due to the combination load case 1, a moment at C and moment at D. End moments is actually asking about the end moments. So corresponding node or beam for that CD is this CD. As our structure is actually 1, this beam 1. So what I'm going to do now is to view the moments. Viewing the moments, these are actually the moments. Then disable the reactions, enable the displacement. I'm gonna go with the moments. So it will actually show me the moments, but here I'm gonna show the value for beam 1. For beam 1, I'm showing the value for the beam 1. So I'm just gonna select results, view value, and ranges, that's beam 1. and then beam result, that is the end moments, and click annotate and it will show it. And you can actually refer this to I'm talking about the moment from here. Like that. So our values, the end moment values or end moments at C, that's corresponds to node 4, that's 87.328 kilonewton kilonewton meter. So that is 87.328. It's okay. And then for the right end, that is node 5, corresponds to the node D. So that's 105.697. 105.697. And then the difference in the next values that we're going to identify is actually according to the load case. Or actually, I'm actually making a mistake from here. This analysis is according to the dead load. So those values are actually wrong. Yes, we're supposed to analyze or to get the value according to the load case number 1. So load case number 1, the left end moment for member CD or for the member 1 in our software analysis software, 167.162. I'm glad I figured that out. 167.162. And moment at D or at node 5, that's 202.324. 202.234. At 202.234. So here we can actually see it, but I am more convenient in locating or identifying those values in the diagram itself, because I'm kinda confused that their values suddenly become negative at this in the table. So we do that again. Result, view values, ranges, beam results, the ends, annotate. Case number 1. So our values for that is correct. 3 to 4. It's wrong. Actually wrong. 3 to 4. 202.324. Then next is we're going to identify the end moments still at CD, but due to the combination load case number 2. So, case number 2. Our load case for that is 58.534, the result, the end moments. So that's 58.534. And for D or at node 5, that's 212.965. 965. Okay, so to that, we're going to identify the actual force in column CF. So, column CF from our reference structure, that is actually corresponds to the beam, the column 5, not a beam, number 5 is 5. So let's proceed with identifying the values according to the wind load, dead load, and combination load case 2 respectively. So let's proceed with identifying the actual forces. The actual force, and same process for convenience and identification of the result values. I'm just going to click result, the view value, and since we are talking about the beam 5 or the beam CF, I mean the column CF, so that corresponds to the column 5 in our structure, in the structural analysis software. So we're going to put 5 and then the actual, the actual, and then click annotate, and then it will give us the value. So what's good at defining which member specifically do you want to view the values, that it will give you convenient and identifying the value at the same time, less confusion, so that's really good about really good thing about this software. So for actual force, due to the wind load only, so I'm gonna change this due to the wind load only, that is negative 31.341. So you can actually still identify the actual forces using these tables, but for my convenience, I want to identify them manually using the view values command. So it's negative 31.341. So we input the value according to the wind load only. 341. It's good. Then next is according to the dead load only, and that's quite big. That's 194.158. 194.158. 194.158. Then a combination load case 2 is number 2, a lot bigger. That's 234. Yeah, logically, because it's already a load combination, so that's expected. So 238.782. 38.782. Sorry, 82 kilonewtons. So we have that's for the actual force in column CF for different load cases. Now let's identify the maximum lift and moment for CD and to where it actually occurs. So I'm just gonna use the same method or same process. We're talking about the maximum left end moment. So left end moment, that's talking about the node C, left end. The node D is actually the right end. The left end moment is talking about here. So let's proceed, and that corresponds to our beam number 1 in our structure. So I'm gonna disable the actual force diagram, and this is 1. Then after that, I'm gonna view the moment, left end moment, then view the values, results, view values, beam 1, then the left end moments, bending ends, disable the actual maximum left end moment for CD. So then annotate, and here identify the maximum bending moments at member CD and to which load case it actually occurs. So what we're going to do now is we're going to run through. Now from the dead load, our left end moment is 87.328. For the dead load, live load, that's 26.414. For the wind load, that's negative 52.422. Load case number 167.162. And for load case number 258.534. So as we have observed, it's actually the maximum left end moment in the load cases are actually at case number 1 with 167.162 kilonewton meters. So we're going to input it here. This is 167.162. 7.162. Then it occurs at the load case number 1. The maximum right end shear. So talking about the right end, so it's at node B, at point B, that actually corresponds in our software. That's node 8. So we're talking about the shear here, so I'm gonna disable the moment and view the shear force, and then I'm gonna view the values, the result values for beam 3. for beam 3, I'm going to specify beam 3, then result values, and the shear. Then annotate. There it it shows me, it gives me the value, shear value at this specific beam. That's beam 3, node connecting node 7 and node 8. So for that, identifying the max, the left and right end shear value for beam AB. So it's actually at point B, at node B, and then identifying to which load case it actually occurs. So again, same process. The dead load, the right end is the right end node D8, or that's actually B. From our reference structure, that is negative 100.335. For the live load, negative 30.348. For the wind load, that's 14, negative 14. The load case number 1, that's negative 192.061, and for the load case number 2, 160. So you can see, it's still in a load case number 1 with the value maximum right end shear, that is negative 192.061. So that's negative 192.061. Am I right? Yeah. Then next is again, it occurs at the same load case as where the maximum left end moment occurs, for CD. So case number 1. Then after that, we are going to identify the displacements at joint B due to the wind load. So we're talking about the horizontal, vertical, and the rotation. So here we're going to disable the shear, and then we're going to proceed with identifying the displacement. And post-processing the displacements. So here in our table, I'm going to use this now, since this is going to be useful. Our table, we will be able to identify the displacement. Displacement of node 8. Node 8, that's actually corresponds to the joint B in our reference structure. Node 8, excuse me. Node 8 there. So it's this is actually according to the wind load. So we're talking about the wind load displacements. So the vertical displacement is negative 0.028. Negative 0.028. Oh no, it's the vertical displacement. While the horizontal displacement it's actually correct, right? Okay, let me view the result. The wind load. Okay. So X, that's 84.649. 24.649. It's our value. 24.649. Then sa vertical is the wind load is negative 0.28. Negative 0.28. And then for the rotation, we have the negative 0.002. And then after that, we are going to identify the maximum span moment for BC beam CD due to the load case. That's number 1. Corresponding number in our structural analysis software. Maximum span moment for beam CD due to the load case 2. So beam moment, I'm talking about the moment, maximum span moment due to the load case 2, case number 2, and I'm gonna view specific result value that is team 1, and then the result value that's the end minimum. Talking about the moment, right? So let's annotate, and then we all can determine the maximum for the span. So maximum value moment for the span is actually 212.965 kilonewton meters. So that's 212.965 kilonewtons per meter. So yeah, so that's it for our video. I hope you learned something about the structural analysis software and how to use them, applying the loads, generating the structure, applying the material and section properties, applying the results. I mean the support reactions. I mean the supports, etc. So I hope you enjoy watching this video, and thank you. Bye.